Before the 19th century, scientists faced a glaring blank spot in their understanding of the world. When a piece of wood burned to ash or an iron nail rusted away, where did the missing matter actually go? The accepted answer for nearly 100 years was a theory called phlogiston. The working assumption was that any material capable of burning contained an invisible fire-like element that simply escaped into the air during combustion. Which brings us to a physical puzzle. If a block of metal burns and releases this escaping fire principle, should the ash left behind weigh less or more? The answer broke the established rules of the time. When metals burn, the resulting powder is actually heavier than the original solid metal. Abstract philosophy couldn't account for this extra mass. Solving the paradox required a complete shift in how experiments were conducted, moving away from simple observation and toward rigorous, exact measurement. That single stubborn discrepancy, a heavier pile of ash, created a crack in the scientific consensus. It forced a new generation of chemists to stop guessing, pick up their scales, and prove the old laws of the universe wrong. The first step toward an answer came from treating the atmosphere as a physical substance that could be captured and manipulated. Stephen Hales, working in the early 1700s, pioneered the practical tools to prove it. He developed a device called a pneumatic trough. By routing a chemical reaction through a tube and bubbling the resulting gas up into an inverted, water-filled glass jar, the gas was trapped. It stayed contained rather than drifting away into the room. By the 1750s, a Scottish chemist named Joseph Black used this trapping technique on heated chalk. He successfully isolated a specific gas that he called fixed air, what we now know as carbon dioxide. Now, imagine you have a sealed jar of this newly isolated fixed air. Curious, what would happen if he dropped a lit match into it or placed a small mouse inside? Black found that the gas instantly extinguished flames and suffocated mice. These experiments confirmed that fixed air possessed unique physical properties that set it apart from ordinary atmosphere. By trapping this fixed air, Black demonstrated that solid matter doesn't vanish when heated. It transforms into an invisible but highly measurable state. With the realization that air was made of different distinct parts, a race began in the 1770s to isolate the specific active ingredient responsible for combustion and respiration. Two chemists, Joseph Priestley and Wilhelm Scheele, working independently, used large glass lenses to focus intense sunlight onto red mercuric oxide. The extreme heat caused the powder to violently bubble, releasing a new, highly reactive gas. If you were to hold a smoldering candle to this pure gas, the flame would flare up with blinding intensity. Why would it burn so much brighter here than in the open room? Both men had successfully isolated oxygen. However, they remained tethered to the scientific consensus of their day, naming it dephlogisticated air, and assuming it was simply an empty vessel for escaping fire principles. Priestley and Scheele had isolated the central element of modern chemistry, but their data remained trapped within the logic of the old theory. They continued to use phlogiston to describe a gas that was currently proving that theory wrong. The shift from qualitative observation to strict mathematics required a different approach, championed by French chemist Antoine Lavoisier. He insisted on conducting chemical reactions entirely within sealed, closed systems, carefully weighing every component before and after. Lavoisier realized that as metal heats, it binds with oxygen. By pulling mass from the air, the resulting ash gained weight. He then burned hydrogen in pure oxygen. The reaction yielded liquid water droplets, redefining water as a compound rather than an indivisible element. Shortly after, precise follow-up experiments on hydrogen gas by Henry Cavendish confirmed this reaction, providing the final data needed to establish the composition of water. By tracking every fraction of a gram within closed systems, these chemists proved that matter is always perfectly conserved. It only rearranges itself. The idea of phlogiston was definitively destroyed by the weight of evidence. The old philosophical arguments simply couldn't survive contact with strict numerical data. The era of guessing based on invisible principles dissolved into the logic of modern chemical equations. Looking back, it raises a question. Was the true breakthrough the physical discovery of oxygen gas itself, or was it the invention of the scientific methodology used to track it? The answer is found in how the pieces fit together. Hales engineered the physical tools to trap gases. Black demonstrated that those gases had unique, measurable masses. Scheele and Priestley successfully isolated the critical element. Lavoisier stepped in to define the mathematical rules governing the reactions, and Cavendish proved that even water was a compound built entirely from those rules. Chemistry crossed the threshold into an evidence-based science because a series of individuals each laid down one solid, measurable fact. They dismantled a centuries-old mystery, not with a single stroke of genius, but with an unbroken chain of precise experiments.